All right, so it's time to tackle the first example where we are going to compute the perturbed versions of eigenvalues and eigenvectors of a problem. And to do so, I've chosen an example that is borrowed actually from structural dynamics, where we could be looking at the vibrations, the frequency of vibrations of a light pole, where we have a large mass at the top of the light pole, which is 1 plus epsilon, and a small mass at mid-height. That was an exam question of my exam of year 2016, or something that was kind of similar. I think in the exam, the large mass was in the middle and the small was at the top, but the problem is quite similar. And so the governing equation for this problem is stiffness minus square of the natural circular frequency times the mass multiplied by the eigenvector or eigenmode shape is equal to 0. And probably you recognize, if you are a little bit familiar with finite element approaches, that the structure of this stiffness matrix is the following, because the first degree of freedom is the bottom one. And so if you displace the first degree of freedom by a unit quantity, you see that the connection with the ground and the connection with the top mass creates twice the stiffness, once and twice, while we see that in order to keep the second degree of freedom in place over here, we just need once the stiffness. All right, same for the rest of the matrix. That's something that is quite easy to get. And the mass matrix over here is a mass matrix where we associate with every degree of freedom the value of the mass that is localized at that degree of freedom. All right, so maybe let's not worry too much where the equations come from in this case, and let's try to solve the problem that we are given. All right, so first, as usual, let's try to look at the unperturbed problem, and based on that, decide whether the problem is singularly perturbed or regularly perturbed. All right, so one unperturbed problem. Okay, so we just replace epsilon by 0. And so we see that the problem we need to solve is a general eigenvalue problem, minus omega squared multiplied by 0, 0, and 1. Okay, like this. Which is still an eigenvalue problem, right? So we would be tempted to say that this is a regular perturbation. Okay, a little bit later, we'll just realize that we did something interesting here, is that in fact we have lost one degree of freedom, or we have lost the mass for 1 degree of freedom. So it means that there's only one more mass, one left, which is equipped with 1 degree of freedom, which is equipped with mass. And that means that that might create some degeneracies with respect to the eigenvalues, but we'll see this in a minute. All right, so let's try to see how we can solve that problem. Maybe just to start, I'm going to rename omega squared. I'm going to rename this lambda, because at some point we will have to use lambda 0 plus epsilon lambda 1, and so on and so on. And it's much better, of course, to use this notation than to write omega squared is equal to omega 0 squared plus epsilon. Then we need to decide what you put here, right? But if you write omega 1 squared, because epsilon is usually a positive number, that's how it's stated in the problem. All right, epsilon is a positive number. You see that here we face an issue, because it means that the first correction is always positive. And that's not necessarily what we want, all right? So I'm just going to rename omega squared. I'm going to rename it lambda. And so the problem that we need to solve is, could put it probably in a smart way, like 2 minus lambda epsilon minus 1. I'm just combining both matrices together, minus 1, and 1 minus lambda for 1 times 1 plus epsilon. This matrix multiplied by phi is equal to 0. All right, and so there is probably a first way to solve that problem, which connects with what we studied before in algebraic equations, right? Because we could write that if this is A times X or times phi is equal to 0, we recognize the problem, and we just have to write that the determinant of this matrix is equal to 0, which means lambda square times epsilon 1 plus epsilon minus lambda times epsilon plus 2 epsilon and minus 1. All right, so this is the characteristic polynomial of the problem somehow. And you recognize here that we have a second degree polynomial equation, which is perturbed because epsilon is a small number. It is a singular perturbation, so meaning that there will be one eigenvalue which can be studied right away with a regular ansatz, and the other one requiring a rescaling. All right, confer what we did in algebraic problems. Okay, I don't want to keep working along that line here because we have just seen some more general theory which can be applicable to more general problems than just a 2x2. Can be applied to problems that are 3x3 or maybe more, and that's the approach I would like to follow. Right. So let's just forget about this by now. If you'd like to keep going with this, of course, you can leave it as an exercise and check or double check that what you have here is similar to what we are going to derive with a more general approach. All right, and so in the more general approach, what we are going to do is to write lambda and the phi, both of them, as a series expansion, and substitute this into the governing equation. All right, so if we do that, what we are going to get is I should probably return to the original writing of the problem, which is over here at the top. All right, so we'll have 2 minus 1. It's going to be a little bit more lengthy than what we used to have because minus, we have matrices now, lambda 0 plus epsilon lambda 1 multiplied by epsilon 0 0 1 plus epsilon, and this is multiplied by phi 0 plus epsilon phi 1. All right, and what is dropped is terms of order epsilon square. We should probably write that that will make it more general, right? We should write that this matrix is K, or I can even write K0, so we know this is something of order 1, and I should write that this is M, the mass matrix, plus epsilon times M1. All right, and so if you identify the different parameters of the different orders over there, you will just realize that M0 is equal to this, and M1 is the identity matrix. All right, so let's keep working with those notations, which will make it much more general. And you definitely recognize some patterns. So if you have to solve similar problems in the future, I also recommend to use more general notations like these. All right, so what we have is K0 minus lambda 0 M0 minus epsilon lambda 0 M1 epsilon lambda 1 M0, all of this multiplied by the eigenvector And then we can expand this once more. And if we expand this once more, what we have is k0 minus lambda 0 m multiplied by phi 0. Then we have k0 minus lambda 0 m0, which is multiplied by epsilon and phi 1. All right, like this. And then last but not least, minus epsilon lambda 0 m1 plus lambda 1 m0 times phi 0. And this is order epsilon square. All right, so once we have this, as usual, we write that the problem is satisfied at each order. And so at leading order, we have k0 minus lambda 0 m0 times phi 0 is equal to 0. All right, so here we have an eigenvalue problem. We need to solve it. It's a 2x2 problem, so we do expect 2 eigenvalues and 2 eigenvectors, right? So that's probably the first thing to do. So if we write k0 minus lambda 0 m, I should probably highlight definition of the different matrices we have. This is m0, this is m1, and this is k0. All right. So k0 minus lambda 0 m1 is going to be 2. I'm just going to right away write that the determinant is equal to 0. And then minus 1. And then minus 1. And then 1 minus lambda 0. The determinant of that is equal to 0, meaning that 2 minus 2 lambda 0 minus 1 is 0, or lambda 0 is 1/2. Okay, and of course you can notice that we only have one eigenvalue. Where does the other one come from? We were expecting 2 eigenvalues. Take a second to think about it. I'm sure you know the answer. That was already hinted by the characteristic polynomial over there. There's one large root that is going to come from large values, from infinity, basically. All right. With this eigenvalue, we can, at least the regular one, we can associate a first eigenvector. All right, so that's the eigenvalue, the first one. We can get an eigenvector. So to do so, we subtract, or we just replace lambda 0 by 1/2. Just rewrite the problem like this. So that's 2 minus 1 and minus 1/2 multiplied by phi 0 is equal to 0. And then, well, you can, if you wish to get details, you replace x0 by x and y. You see that 2x minus y should vanish out, so y is equal to 2x. Of course, you expect the second equation to provide the same. You can just check it if you wish. And so one possible choice, if you want to make things normalized, is to choose phi 0 is equal to 1/2 and 1. Okay, it's just a way to pick the eigenmode. In principle, it is multiplied by a constant, which I choose equal to 1 here for normalizing purposes. And my normalizing habits is such that the largest value in phi is equal to 1. Normalized such that, if you want to pick any other normalization, of course, for phi, you feel free to do it, such that the max of the different entries in phi is equal to 1. All right, so we got it. then there should be another route, but let's take care of the second route a bit later, all right? Because we know anyway that what we do can be done or needs to be replicated here for every single eigenvalue. All right, so after having solved the unperturbed problem here, we can solve the problem at the next order. And at the next order, it says same operator. All right, this is something also that is quite common in perturbation techniques. We have the same operator, but applied on phi1. Same operator on phi1. I can push this to the right-hand side. And so we have equal 0, lambda 0 m1 plus lambda 1 m0 times phi 0. All right, so you recognize here things that we discussed in the first video of this series, where it looks like the previous eigenvalue problem, but it's not really an eigenvalue problem, right? We have the same operator on the left, but the right-hand side is not equal to 0. So this is not a homogeneous problem, not a homogeneous problem. All right, so this is not really an eigenvalue problem, but yet we know that the determinant of the matrix over here, we know that the determinant is equal to 0 because this is exactly what we just wrote. All right, so we need to make sure that there is no contribution on the right-hand side, which is aligned with the corresponding eigenvector, which is phi 0. And by the way, you just realize that if we just project everything on phi 0, then because all matrices are symmetric, that left-hand side is equal to 0 because of first order. And this is also equal to lambda 0 m1 lambda 0 times phi transposed, because we multiply by phi 0 transposed left and right in the previous equation, plus lambda 1 phi 0 transposed m0 and phi 0. Okay, from this we can get lambda 1. These quantities can be estimated easily. You see m1 is the identity matrix, so we can compute phi 0 transposed phi 0, which is 1/2 1, 1/2 1. So that's 1/4 plus 1, 5/4. All right. Meaning that this is equal to 5/4. Lambda 0 is 1/2. And the last element over there, we need to replace m0, okay, which is actually nothing but extracting. You see that m0 is 0, 0, 0, 1 over here. So we just do extract the second element from phi 0 when we do that. So phi 0, m0, phi 0 here is equal to 1. All right, and from this we can obtain that lambda 1 is equal to -5/8. All right. And this is the first perturbation to the eigenvalue. By the way, you see it is negative, and so it's good that we made the change of representation and didn't use omega, as we could have done from the beginning otherwise. All right, so once this is done, what do we do then? We reconsider the equation before projection. All right, so here there was a projection. We consider the equation before, replace lambda 1 by that value. All right, so on the left-hand side, we have in fact something that we have already computed, right? Because we have the same matrix as the one before. So that's the same operator, minus 1, 1/2, okay, multiplied by phi 1. And this should be equal to lambda 0 m1, so 1/2. I'm going to write it in full, because m1 and m0 start being quite far away. This is identity matrix, minus 5/8 times m0, 0, 0, 0, 1. All right, so probably we could put everything in 8, like this. So we have 4 minus 5, that's minus 1. Then we have 0, we have 0. And oops, there's something I forgot to do, sorry for that, is to multiply all of that by phi 0. So minus 1, 0, and 0, and in the bottom right corner we have 4 minus 5 again. I made a mistake, I'm sorry. Let's recap. So here, top left corner, we have 4/8 minus 0, that is 4/8. Then we have 0 minus 0, same here, 0 minus 0. Then we have here 4/8 minus 5, so this one is minus 1/8. And this needs to be now multiplied by phi 0, which is 1/2, 1. All right, so the right hand side here is 1/8 multiplied by 4 times 1/2, that's 2, and minus 1. All right, and you see that this makes sense. We made everything in such a way that there is no contribution which is aligned with phi 0 on the right hand side. So if you compute again phi 0 transposed times 2 and minus 1, you see that they are indeed orthogonal to each other. All right, that's 1 minus 1, so this is 0. Or in other terms, you can also just realize that in that equation, the equation that we obtained here, the second equation is exactly the same as the first equation, all right? So you multiply in order to get the second equation here. From second to first, you multiply by minus 2 times minus 2. And this is exactly what you do on the right-hand side too, all right? If this was not the case, it means there is a problem somewhere. Check your computations. All right, and so what we can do now, we can solve this problem and just say if we write that phi 1, if we just write it like before, x and y, this is 2x minus y is equal to 2/8, that is 1/4. All right. So probably we could choose, if I choose just 1 for y, let's check, y is equal to 1. It means that 2x is equal to 5/4, meaning that x is equal to 5/8. It is well smaller than y, and so this satisfies my standard usual normalization principle, all right? So it means that the corresponding mode shape is 5/8 and 1, plus any additional constant, arbitrary constant, multiplied by phi 0, okay? And so here you see that k, we can choose k in an arbitrary manner. K is arbitrary. could be, for instance, chosen as k is equal to 0 or k is equal to -1, whatever. The only limitation you have on k is that it shouldn't be of order 1 over epsilon. It shouldn't be a large number. All right? So if I had chosen, for instance, k is equal to 0, I'm going to show you now that no matter what you choose for k, it results in the same eigenvector. That seems to be a little bit paradoxical, but this is what we get. So we have phi 0, the eigenvector, the eigenvector phi is phi 0 plus epsilon phi 1, and phi 0, we have just seen this is 1/2 and 1, plus epsilon times phi 1. I just chose k is equal to 0. All right, so we have 5 over 8 and 1, like this. And then let's put everything together. This is 1 over 2 plus epsilon 5 over 8. And this is 1 plus epsilon. Okay, that's the eigenvector. That's the eigenvector we have. Maybe we can multiply everything by 8 to make it more clean. 4 plus 5 epsilon. And here we have 8 plus 8 epsilon. All right, that's the eigenvector. If I had chosen, for instance, k is equal to -1, why not? That's also a possibility. In that case, we would have obtained phi 1 is equal to 5 over 8 minus 1/2. That is 5 minus 4. That is only 1 over 8. And 1 minus 1, this is 0. Okay, and what I want to claim is that this eigenvector, the one that we obtained by combining phi 0 and phi 1, is in fact the same as the eigenvector we had by choosing k in a different manner. All right, let's see. This is phi 0 plus epsilon times 1 over 8 and 0. And so if we put 1 over 8 before, we have 4 plus epsilon. And we have here, in the second line, we have just 8. All right. And so clearly, of course, these are not the same two eigenvectors. But what I just want to say is that they point in the same direction in the space. They are not normalized in the same way. All right, clearly they are not normalized in the same way because even the second component here is not the same, right? So if we, for instance, take the first one and divide the first one, by 1 over 1 plus epsilon, the first solution, we have, so you remember that 1 over 1 plus epsilon asymptotically is 1 minus epsilon and so on, right? So is asymptotic to this epsilon square. All right, so instead of dividing by 1 plus epsilon, I will just take the first eigenvector, all right, this quantity, and 8 plus 8 epsilon, and I will just multiply this by 1 minus epsilon, all right? Or divide by 1 plus epsilon, this is the same story, all right? So which means that the second coefficient here will be 1 plus order epsilon square if we want. All right. And the first coefficient will be 4 plus 5 epsilon, then minus 4 epsilon, plus terms of order epsilon square. And what do you see? You see indeed, these are the same two quantities. Oh, sorry, I just wrote 1 for the second, but that's how you realize. you can make a mistake. You see we have exactly the same quantities. All right, so just this was just to emphasize the fact that no matter how you choose k, what you end up with is the same eigenvector. It's just that at the end of the day, it's normalized in a different manner. All right. Well, that's it. We just forgot to focus on the large eigenvalue. So far, we just focused on the small eigenvalue, the one that was in the neighborhood of 1/2. And so maybe let's just summarize and say lambda is lambda 0, which is 1/2, plus epsilon lambda 1, which is -5/8. All right. So that's the solution of the problem, right? This all together with the corresponding eigenvector. All right. So let's focus now on the large root. Large root. Let's start again where we were. We need to find, of course, the right scaling for the large roots. All right. Probably let's copy something we can use to understand. Let's copy all of this and restart from there. Okay, the large eigenvalue. All right, so to find the large eigenvalue, what we could do is probably try to rescale. We can just give it a try, as we did first with algebraic equations, right? There are techniques to find the right order of magnitude, as we did with finding the right balance, do pairwise comparison, that kind of stuff. All right, but I'll just start here by assuming that this is large and this is of the order of magnitude of 1/epsilon. And so I can write lambda tilde divided by epsilon, and that would be the rescaling. All right, rescaling. And so it means that instead of using lambda 0 here plus epsilon lambda 1, which actually comes from lambda, I'm going to write over there lambda tilde over epsilon. All right. And if I write lambda tilde over epsilon over there, let's just rewrite something similar to what we did earlier. And you will see what we get. So we should probably also make it clear that lambda is of order 1. And also it should be different. It should be different from 0. All right, so what we have there is k0. Let me just multiply everything out by epsilon, all right? Just because I don't want epsilon in the denominator. That's something you should be allergic to when you deal with perturbation techniques. All right, so this is epsilon times k0 minus lambda tilde, which I'm gonna expand as this, okay, a regular expansion for the rescaled version of the eigenvalue, times m0 plus epsilon m1, and all of this multiplied by phi 0 plus epsilon phi 1. And that is order epsilon square. All right, so definitions of m0, m1 hasn't changed, and k0 neither. So we keep the same definitions as those we used earlier. Just need now to expand. I will start with lambda 0 tilde m0, because this one is first order. I'm just looking for the terms that are first order, and this is the only one, in fact. Multiplied by phi 0. And then we are going to collect the other terms, which are of the following order. So definitely we'll have the same operator applied to phi 1. Then multiplied by epsilon, of course, plus epsilon k0 phi 0. And then we have minus lambda 0 m1 times phi 0. There's also an epsilon out there. And lambda 1 m0 and phi 0. And there's also an epsilon out there. All right. And all of that is equal to order epsilon square. Okay, and we can clear what we had before. This is kind of similar, but not exactly the same. One way to make sure there is no mistake at this point is that you realize that you see 0 plus 0 plus 1. That was one of the advantages of writing the problem with matrices as we did. This is order 1. This is order 1. 0 plus 1 plus 0, this is order 1. Here we have, okay, this is supposed to be order 1, of course, because it comes from the k0, but we are fine with this one. 0 plus 0 plus 1, this is order 1. And 0 plus 0, this is order 0. All right, so it should be all right. At leading order, what do we have? We have that minus lambda 0 tilde times m0 times phi 0 is equal to 0. And you see that the matrix here, m0, is already singular. And that's good for us, is already singular. All right. And when this is the case, then there is something specific. Instead of seeking, or instead of getting the solution of the problem as starting first by the eigenvalue and then the corresponding eigenvector, which is what we usually do in classical calculus, then the correction to the eigenvalue, and then the correction to the eigenvector. Unfortunately here, you see that there is no way to get it at leading order. No way to get this at leading. But it shouldn't be too much of a problem. No way to get this at leading. All right. What we need to say, however, is that phi 0 is such that m0 times phi 0 is indeed equal to 0, meaning that phi 0 can be chosen as, for instance, 1, 0, if I want to use my regular normalization condition. All right, so you see here, we start by computing first the eigenvector. And lambda 0 will come at next order. All right, so let's keep going with the next order. Order epsilon. What do we have at order epsilon? We need to collect the different remaining terms. So lambda 0 tilde m0 phi 1 with a minus over here. I'm going to put all other terms on the right. So there will be minus k0 phi 0 plus lambda 0 tilde m1 phi 0 and plus lambda 1 tilde m0 phi 0. All right, so now there are a few things we need to compute. This, maybe this. All right. First thing we do observe is at leading order, what we had solved is m0 phi 0 is equal to 0. All right, this is also here, meaning that this last term definitely will vanish. All right, so that's good. m1 times phi 0, m1 is the identity matrix, so this is 1, 0. And then we need to get rid, ideally we need to get rid of phi 1. And so remember what we do when we come to the next equation. The first thing we should do is to compute a scalar problem. So we do project on phi 0. All right, so projection on phi 0. And if we want to project this on phi 0, what we have is minus lambda 0 tilde phi 0 transposed m0, okay, times phi 1 is equal to minus phi 0 transposed k0 phi 0 plus lambda 0 tilde phi 0 transposed m1 phi 0. And you see this is, well, magic. Well, it's because we have the right order or the right scaling for the eigenvector. You see that lambda 1 tilde has disappeared because of this. Lambda 1 tilde has disappeared. In principle, we should expect, or we would expect to get lambda 1 at that order, but exactly as we didn't get lambda 0 at the previous order, lambda 1 will be repelled to the next order. So we will use the next equation to get lambda 1. Okay, so furthermore, we recognize here something that should be equal to 0 because m0 is symmetric. All right, and because m0 is symmetric, we still have m0 phi 0 is equal to 0. So this disappears, and we have a very simple equation then to determine the lambda 0 tilde. All right, this is nothing but the norm, the squared norm of phi 0 because m1 is identity, so that is equal to 1. And phi 0 transposed times k0 times phi. We should probably compute this on the back side, like this, 1, 0, and 1, 0. Okay, what we do, of course, we do extract the first term, and this is equal to 2, meaning that lambda 0 tilde is equal to 2. All right. Let's just keep the leading order for that root as an exercise. You want to keep going with the determination of lambda 1. But if you want to do that, then you need to rewrite the equations at the following order. All right. So what we are just going to write here is we found the problem. We found the solution of the problem. And we can say that lambda is equal to 2 over epsilon, because we're coming back to the original units of the original quantities of the problem, plus something of order 1, and phi 0 is 1, 0, plus something that is of order epsilon. All right, and at order epsilon here, we haven't really finished. We could go to the determination of phi 1, but it doesn't really help as long as you don't go to the next equation and at the same time compute lambda tilde 1, all right? Just to make it consistent. What this says is that we have, in the problem, we have then a second vibration mode, which is like this, and where the first degree of freedom is equal to 1, and because of a small mass over there, because of a large mass, which is 1 plus epsilon over there, and we have a small mass over here, actually what we do observe is that we do observe a mode where the mass here does not move, and only the mass in the middle move. All right, so if it was really a light pole, the type of mode shape that you would observe is something that would be like this, where it vibrates left and right. Because it has almost no mass, and you remember that the frequency is stiffness over mass, if the mass goes down to 0, you see that the frequency goes to infinity. And this is why we have a very large eigenvalue, omega square. We have a very large eigenvalue, and the eigenvector looks like this, so 0 at the top and 1 in the middle. All right, so it was just to make the link with the physics. I hope you understood exactly the derivations. There will be a few more exercises. Eigenvalue problem is quite important. You see them in optics. You see them in eigenvalue solution of linear differential equations. Again, that's really important because this is one way to sort out the different orders of magnitude corresponding to, for instance, time scales in this case, but it could also be length scales in other problems, all right? So you will encounter those problems in the future, so keep going and don't forget to practice and keep going with the next videos. Goodbye.